Okay, so now we talk about transformation. So what exactly we want to do in the transformation? So we should understand first. So if you have already attended the first lecture from Professor Ekel, you would have already seen this diagram. So where we have stator, it's not perfect circle. So you would have a stator, and then on the stator, there are like 3 windings. And yeah, so there will be 3 windings basically. And of course there will be rotor. So I'm not very good at drawing, so forgive me for my bad drawing. So let's say this is your rotor and this is your rotor axis. Okay, so this is our phase A winding, this is phase B winding, and this is phase C winding. Okay, so this is phase A, phase B, and phase C. And of course, the opposite end, you will also have some winding which will be, so like there will be another winding. So I would use different color. So on the opposite side of A, there will be another winding which will be called A dash. And the C side, there will be like C dash, and opposite to B will be B dash. So this is, yeah, so this B dash basically represents our negative axis and the B represents the positive axis. So like that, A also represents positive axis and B represents our negative axis for the A. Is there any question now? Okay, so this is just the diagram which you would have already seen in the lecture. And now, now let's see what we can do with this. So, and it's very important to note that this is our state space representation. This is state space representation. You might have seen some the phasor diagrams also, right? So don't get confused with the phasor diagram here. In phasor diagram, what you would have is you will have A axis this side, the B axis this side, and the C axis this side. So in power systems, if you see, you will see that the A axis, like in power systems, we basically draw many places phasor diagrams only. And in phasor diagrams, you will have A axis this side, B axis this side, and the C axis that side. So this is your phasor diagram. So I will tell you the difference. This is phasor diagram. And in this phasor diagram, we see by what angle the other phases are lagging. So if you see here, the B axis is lagging A axis by how much degree? 120 degrees. So here B axis is lagging A axis by 120 degree, and the C is leading A axis by 120 degree again. Okay. Here also we have 120 degree angle. So I would draw it in the state space representation. So this is your A axis, this is your B axis, and this is your C axis. And here so we do not tell the B axis is leading A axis by 120 degree. Here it is in a state space. So it is placed 120 degree away from B axis and and anti-clockwise. So it is the B phase or the B axis is placed 120 degree anti-clockwise. Okay, so here the B axis is actually physically placed there and it stays there. So this is in a stationary frame, and this phasor diagram is in a rotating frame actually. Okay, so so the state space representation is this, where you have B axis placed 120 degree anti-clockwise And so I can just write it also here. So it is placed 120-degree anti-clockwise from a-axis. And here the B is B lags A by 120-degree. Okay. And you can imagine, and here what happens is, if you want to visualize these two in a different perspective, you would see that this A axis does not move, like the stator does not move, right? The stator is remaining fixed, it does not move. And in this phasor diagram, what happens? This whole phasor diagram is moving with the speed omega. So that's the main difference between the state space representation and the phasor representation. So in phasor representation, what happens? We use here magnitude and the phase difference between the two phases, and the whole phasor diagram, if you see it rotates. So we never draw it in rotating because it's not difficult. It's impossible to, like, it's not easy to understand if the whole phasor diagram is rotating. So since everything rotates with the same magnitude, and the phase difference, and if you want to find the instantaneous value, okay. So let's say from phasor diagram, you want to find the instantaneous values. What you can do is you can draw the x-axis. So this is your x-axis. And at any moment, you can just find the component of the A, B, or C on the x-axis. Okay, you can find the component of A, B, or C on the x-axis, and that will give you the instantaneous value of the ABC for that moment. So, and it rotates. Okay, so when, let's say, A rotates by 45, so I'll draw the ABC also here. So let's do the waveform. I'll use different colors for that. So let's say black is the first phase. And then we have red is the second phase. So this is our 90-degree, and so probably here we will have the another. I'll just draw it roughly. There is a simple way you can draw. I'll try that one. You make a triangle. You make a triangle. You make a triangle, and then you add the top. Like this, and like this. Okay. And then you can just draw axis in between. This gives you the ABC. So probably like this, it goes. And here you can assume this is your VA. Oh, no. Comes here. So this is your VA, VB, and VC. So this is also one way. If you struggle to draw ABC, you can draw like this, and you can see here the A voltage is leading B voltage by 120-degree, and B is leading C by 120-degree. And now let's see. So if you see in this moment, so the state space representation, we have the stationary frame. So this does not rotate. So this is your stationary frame. So it is fixed. It does not rotate. And its instantaneous values its instantaneous value is on that axis itself. So it means for the a parameter, so if it is positive, so let's say at this moment, so it is positive and peak, we will have the value on a here. And the next other moment, let's say it is here. So and then what will happen, the value of a will be negative and it will be on this side. Okay. And when we see the value of the b, so at the moment where we have let's name it like this. So let's say we name it the 3 instances. So this is instance 1, 2, 3 points. So for the first point, our VA is positive, so we have VA here. Our VB is negative, and so our VB will be somewhere so our VB will be somewhere here. And again, VC is negative, right? So VC will be also on the negative axis and it will be here. Okay, so if you want to visualize like that, so in a stationary frame, this whole axis is not rotating, it is fixed. That is a state space, and you can find the resultant. You would see the you can find the resultant for these vectors, and you then will find your resultant like in pointing in this direction, right? Yeah. So this is for the first point, and this is our resultant for the first point. But if you want to see for the phasor diagram, you would see we need to do a projection for those quantities. So you would see like the A is already at maximum, so it will stay there, and the B we need to do a projection. So we need to project it back, and you will see it's already negative, right? If you want to find instantaneous value of B, you will see it's already negative, and the C is also negative, and actually they will be the same. Yeah. So, and in this, so it happens like that. When we go to the second point, so it has rotated by some angle, and I think that angle is 60 degree. I would, it can be any angle. So now the next time you want to draw, you want to find the points for the second, for the second case, you want to find the points on the state space, then we will do like this. You see the A phase is positive, and it is somewhere so the A point is positive but less this time, so this is your second point. And then the B phase is also positive, so it is somewhere here. And then the C phase is negative and it's maximum. Okay, so negative and maximum means it will be somewhere here. So you can find the resultant which will be pointing in this direction. So this is the resultant for the second case. So now you see the resultant is rotating, right? The resultant is rotating. So it has rotated anti-clockwise. And this is how your flux rotates. This is how the flux in the machine rotates. And what happens? The rotor tries to catch this flux. Okay. But if you want to visualize this second point in the phasor diagram, then what you need to do is you need to rotate this whole phasor diagram by 60 degree. Okay. So it means now this is your x-axis. This is your x-axis. And then let's rotate this whole phasor diagram by 60 degrees. So the A will be here. It's not 60, it's less than 60. So A will be here. And probably B will not be there. Yes, the C will be here. and then the B will be here. And you want to find the instantaneous values, then you can find the projection on the x-axis. And you can already see the B and A and B is positive, which you can also see in the second point, right? The A and B is positive, and then the C is maximum but negative. So do you see the difference? It just, when I was a student, I was confused, like why do we do one, why we write in phasor diagram, we write like B lagging A by 120 degree, but in the state space, we write B like 120 degree leading A axis. So this, I used to get confused, and I thought like you may also see some places like this diagram, and some places you may see diagrams like this. And so don't get confused, both are right. Both are right, perfectly right. It's just the way you write it, it's different. Okay. Okay, so this was just for understanding what is a state space representation and what is a phasor diagram representation. But in both cases, if you see, the resultant rotates with omega. If you see the resultant of the whole voltage or flux, so what's happening is the whole flux is rotating, right? So in a stationary frame, what's happening? Our flux is rotating with omega. And if you see for the point 3, so I'll not draw the phasor diagram now. I will draw the state space. And let's see for the point 3. So for point 3, we have B as negative. So it is here. And then this is our 3. And and the C is 0. C is 0 means here. And B is positive. B is positive means here. And you can see the resultant is this way. Right? You can just do the vector summation and you will find the resultant. So it has again rotated by this. So what's happening as the time is moving, your resultant flux in the ABC frame is also rotating. And it's rotating anti-clockwise with this voltage sequence. But if you change the voltage sequence, then it will rotate other way. Like what I mean to change the voltage sequence, let's do it. Let's do it. So this is with the voltage sequence you always have in the grid system. You always have the first A voltage. Is there some? Hello. Yeah. Trying to record the video, so if you miss something, you can always see the video and of course ask me. Okay, so this is the voltage sequence you will see in the grid. And now let's reverse the sequence. When I say reverse the sequence, what first thing comes to your mind? In which places the sequences are reversed? Have you heard of negative sequence? Have you heard of negative sequence? Like in power systems, you might have heard positive sequence, negative sequence, zero sequence, right? So the negative sequence, what happens is, we know that we are rotating in clockwise direction now, right? For the positive sequence, our omega rotates, like the rotation of the vector is in anti-clockwise. And when we rotate in other direction, we call it as a negative sequence. So that is a clockwise direction. So in negative sequence, what happens? Your A, B, and C sequences are reversed. Like the voltage sequence are reversed. So this is for your positive sequence. So I can also write here positive sequence. And let's draw the phase state space diagram for negative sequence. So negative sequence voltages. Okay, so again, I will try to draw triangles. So this is your VA, VB, VC. No, sorry, this was the positive sequence, but now it will be A, B, A, C, and B, because we have interchanged the C and the B. Okay, so in the before we had B first, right? And now we have a C, then we have B. And let's take again 3 points. So let's say so let's choose the 3 points. So 1 point here, another point can I undo? Okay, I did some mistake. But I'll try to fix. So the green color. This is our point 3, point 1, and point 2. And we draw the phasor diagram again. Look, not phasor diagram, state space diagram. So this is our A axis, this is our B axis, and this is our C axis. So for point 1, we will use red. And so for point 1, so can you tell me where should I put the, like where the value of A will be? It will be on this side, or it will be on this side? Positive side or negative side? Positive side. Good. So we have A over here. What about B?
Negative.
So B is on negative side. So negative side is here. And and it seems maximum, so hopefully it seems good enough maximum. Okay, and what about the C? Is it positive or negative? Positive.
Positive.
So it will be here. And where will be the resultant? Negative B.
Negative B.
Yeah. So this is our resultant, right? So this is the first case. Let's see the second case, and try to use green color. Yeah, this is first time I'm working on these this laptop, so okay, hopefully it's good. So now tell me where the C should be for the second case. Positive or negative? So it's positive, right? For the second case, C is positive. So we have C positive and it seems maximum, so we keep it here. What about A? A is negative, so it will be, A is negative, and it will be here. And what about C? No, like C is done. B is, yeah, what about B? B is again negative, so here.
Negative.
So where will be the resultant? The positive C axis,
C.
right? So we have resultant here in this direction. So now do you see one interesting thing? Now we are not rotating anti-clockwise. Which direction we rotated?
Clockwise.
Yeah, so this was initial phasor, and now this is the phasor. So it has rotated which direction? This way. Mhm. Let's see the third point. So I would use some other color. There are a lot of colors, so let's use this one. So for third, so we can see B and C is positive. So B will be here, C will be here, and then our A is negative. So negative A is here. So again, we will have resultant in A negative side. And this time also it's rotated clockwise. So that's the main difference between negative sequence and positive sequence. And that's a name, we rotate anti-clockwise, we tell positive, we rotate anti-clockwise, we say negative, because it's just a sign convention. It's just that anti-clockwise we consider positive, clockwise we consider negative, and hence we call it positive sequence voltage, negative sequence voltage. And zero sequence does not rotate. It stays where it is. So the zero sequence is always there. It's just a magnitude, which it's a DC, the DC does not have frequency. So the zero sequence is a DC value, positive sequence rotates anti-clockwise, and negative sequence rotate clockwise. So yeah, so this was about, this is just to tell you what is the main difference between positive sequence, negative sequence, and the zero sequence. Okay, so we can write like positive sequence voltage, it rotates anti-clockwise and negative sequence voltage rotates clockwise, and zero sequence, it's a DC value, so does not rotate. If DC starts rotating, then we call it, we don't call it a zero sequence. And this is zero sequence, and it remains constant for all three phases. If you already know the power systems, like the positive, negative, and zero sequence components, so you would see that the magnitude for all zero sequence components in three phases are same. Okay, so is this clear, or is there any question? If you have questions, you can ask, or else we can proceed further. Okay, so no questions. Let's go to the transformation now. So this was about the feeling of the system, whether it is positive or negative. Now let's see what do we need to do? The transformation. Okay, so why do we need transformation? First, we should understand that. So if you see, so of course we are doing transformation for AC system. We do not want to do any transformation for DC system, right? We just want to do transformation for AC systems. And why do we want to do transformation for AC system? So have you ever worked on controller or anything? Anyone worked on controllers? Have you controlled DC motor or anything in your childhood? Maybe you wanted to control the speed of motor and then you change the voltage. And have you ever done something like that? Or have you worked with, played with some toys? The car racing toys where you accelerate the car and you decelerate the car. So maybe if they have DC machines, DC motors there, then you would use the DC voltage. So the thing is, controlling DC loads is very easy. Why is it easy? You just have to change the magnitude, right? For DC voltage, what do you need to change? For DC load, you have to just control the DC magnitude. Have you ever, do you need to worry about the phase of the DC? No, you just put the correct voltage and it works. So controlling DC is very, very easy. Okay, it's much easier than AC. When it comes to AC, there are so many things you have to consider. The first thing is magnitude. For sure, your magnitude also should be correct. Your phase should be correct, right? Your phase difference should also be correct. And your omega should also be correct. Your angular speed should be also correct. If you want to control something, let's say you want to connect your converter to the three-phase grid. So you have to synchronize first, right? And for synchronization, what you need to make sure? You need to make sure your converter produces exact same voltage to the grids. Then only you can close your contactors and connect to the grid. Otherwise, you cannot just give any random voltage and connect to the grid. You may burn the whole system. So you have to take care of your magnitude, you have to take care of phase, and you have to take care of your angular speed also. So that is, so and this introduces also some complexity in the control. If you want to control things, so you have to control your, let's say you want to control the currents in phase with the AC voltage, then you have to control the current so that it is perfect in phase with the voltage. If you want to make the just active power, no reactive power, so you have to control its phase, that it should be exactly in phase with the voltage, right? Magnitude, it's okay, you get from some controller. And so when you want to control the magnitude of AC parameters, then you can see the Bode plots, which you will see in the later. You will see in the later exercises that the gain is not perfectly one. So if you want to control the AC frequencies, like AC quantities, you would see that for those frequency, gain is not perfectly one. It means the reference what you give and the actual value what you see, the gain might not be one. If you want to make it one, then there is one way you can do you can use a resonant controller. That's a resonant controller is like it filters the particular frequency component only, and then you can control over it. But that's, again, people are not trying to do that. So that was the previous thing. Long back, people used to do resonant controller, which can control the particular frequency. So let's say you want to control the fundamental frequency, which is 50 hertz. So you want to control the 50 hertz component perfectly. So people used to use resonant controllers in 3 phases. So they used to have 3 resonant controllers for each phases. And that's is not really good, I would say, especially when we see maybe passivity plots or the dynamic plots. Yeah, but it's complicated, little bit more complicated. So, okay, so that was the thing. So let's say we have 3 controllers for 3 phases. Will it be more simple if we make this 2-phase? Instead of controlling 3 independent phases, will it be more easier to control 2 phases? It's easy to control 2 phases compared to 3 phases. And will it be even more easier if we make those AC quantities DC? Then voila, it's like the AC quantity, if the AC quantity becomes DC, then you just have to worry about the magnitude, right? You just don't worry about the phases and other stuff. So that's the main objective of transformation. So what transformation, why we use or why we need this transformation? We want to basically get our fundamental components. We want to get the DC value for the fundamental component, and that's why we can control those DC values very easily and very simply, and we can perfectly track those the reference value. Like the reference value, if you give 1 per unit, the actual value can also go to 1 per unit. Because it's a DC, there is no frequency, so the gain problem if you see the first order system, the gain is perfectly 1 there. So for DC, yeah. So that's the main objective. So main objective of our transformation is we want to convert our 3-phase system to 2-phase system. 3-phase system to 2-phase system. And this 3-phase system is your ABC system, and two-phase system is your alpha beta system. Okay. And of course, we have also zero sequence, so we write alpha beta 0. So that 0 is anyway, it's the same in either ABC frame or alpha beta frame or DQ frame. It's going to be same. Okay. And this is, of course, the AC frame. So this is your alpha beta but stationary frame. Stationary frame, which is and then the here, what is here, the quantities are AC. Here the quantities are AC. We will see that. We will see that. Now, okay, we have a chat. And there is a yes. Okay. So now, this two-phase system, which is your AC system, we can get it back to two-phase DC system. Okay, so two-phase DC system, and this is your rotating frame, and quantities are DC. Okay, so this, and if you see here, okay, this is rotating frame, and which is called DQ0 frame. So this is called DQ0 frame, and I would not say DC here. I would like to be careful. So I would say here fundamental quantities, not the quantities. That would be wrong. That would be perfectly wrong. So we just say fundamental quantity. Okay. And here also fundamental. But again, fundamental quantities, here all quantities are actually AC, so that's not a problem. Here alpha beta quantities are AC. And in the DQ frame, we have the fundamental quantities DC. There is also, if you use theta is equal to theta positive. Yeah, so this is one thing we will see in the later, but the main objective is we want to convert three-phase system to two-phase system, and then we want to get the DC so that we can control the thing. Okay, and this ABC to alpha beta transformation is called a Clarke transformation. And alpha beta to DQ0, it is called Clarke transformation. Okay. And of course, if you do reverse, the reverse means DQ0 to alpha beta 0. It is called inverse Clarke transformation. And if you do alpha beta 0 to ABC, oh, sorry, this is inverse Clarke transformation. And this is your inverse Clarke transformation. Okay. Okay. And now let's see how we can do it. So this is our main objective. Like, it would be really nice if we can get our fundamental components DC, and so that it's easier to control it. Okay. Let's see how to do it now. So let's take the first Clarke transformation. And we will use here state space representation. We will not use phasor diagram representation. Okay, so you should always consider here the state space representation. So we have A axis in this direction, B axis in this direction, and C axis in this direction. So this is your A, B, and C. So to transform this three-phase quantity to two-phase quantity, it's very simple. We just know the x-axis and y-axis, right? So this is your alpha axis, this is your beta axis. Here alpha axis is your real axis and beta axis is your imaginary axis. Okay, and we just find the components of these vectors and then we are done, right? So the alpha axis is aligned with A axis. You should know this, okay? And the beta axis is perpendicular to A axis. So you want to find the component of the quantities along the alpha axis, and you want to find the components of quantities in beta axis. So we just need to do a resolution, like we just have to resolve the vector, right? It's pretty simple. So this you already know it's 60 degree, and this also you know it's 60 degree, right? So if we want to find the F alpha, so I just write here F can be anything. It can be current, it can be voltage. So I just try to write like a F. Okay, you can write V alpha if you wish, so no problem. And so here what we can do is, so F alpha is FA for sure, yeah, because it is along that x-axis, and then we resolve this C and B. So if you find this resolution, so you can see it's a 60 degree, so hence this is going to be minus FC cos 60 degree. Why minus? Why minus here? It is in the negative axis. It is in the negative alpha axis. That is why we have a minus. And the same way we can write FA cos. Oh, sorry. Thank you. So FB cos 60 degree. And you can just, so what is a cos 60? One by two. So this is FC by 2 and then FC by 2. This is fine. We'll come to that later. Now tell me what is F beta. So what is the beta component of A? 0, because it's perpendicular to that. Okay. What about the B component on beta? FB sine 60. And we write it positive, right? Because the component is on the positive axis. What about FC? And what is sine 60? Root 3 by 2, perfect. Okay, so this is your F beta. And F naught, which is a zero sequence. So the zero sequence is very easy. We just add all these quantities and divide it by 3. So we know that there is one quantity which is same in all 3 phases. Okay. So I mean, yeah. So in simple way, we can just write it like this: FB FC by 3. If you want to understand why it is like this, so let's see it again. So let's say we have FA equal to FA dash plus F naught, FB equal to FB dash plus F naught, FC equal to FC dash plus F naught. So the zero sequence is same in all phases. You should remember that. same in all phases. Okay. So the zero sequence is same in all the phases. It can be DC, it can be AC also. Also remember that. Not necessary it has to be AC. No, not necessary it has to be DC. It can be AC also. Mm-hmm.
It's FCO2 and FCO2.
Yeah, thank you again. Yeah. So this is how you find this ABC, because like the zero sequence, and this FA dash, FB dash, FC dash will be either positive sequence or negative sequence. So positive negative sequence, zero component is always zero. So they add up always to zero. So yeah, and that is why we find it like this. So if you add all these three, is FA dash, FB dash, and FC dash is going to be zero. So FA dash plus FB dash plus FC dash is always zero. And that is why you can find F naught like this. Because these FA dash, FB dash, or FC dash, these are either positive, negative, or both sequence components. Okay. These are either positive, negative, or both sequences. Both means positive or negative. And then the zero sequence is this one. Okay, so this is so this is how you can find your transformation equations. It was easy, right? I think it's easy. Now we want to make a matrix out of it. Okay, so you can also write the matrix very easily. So we want to write F alpha, F beta, F0 here, and then something, and this is your F A, F B, F C. So can you help me fill this matrix? So what's going to be the first element? 1. Second?
1 by 2.
Minus 1 by 2. The third? Okay, and then this second row, the first element?
0.
0, because there is no FA. What about the second?
Root 3 by 2.
And the last, the second row?
Minus root 3 by 2.
Perfect. You all are very good. What about the last row?
1 by 3.
1 by 3, 1 by 3, 1 by 3. This is the matrix. This is your Clarke transformation matrix. You may have some questions, but I will come to that later. Clarke's transformation matrix. And if you want to find the inverse Clarke, you can always find this inverse, right? If you want to find the inverse Clarke from ABC to alpha beta 0, you can do the inverse. So I can write this like this also. F alpha beta 0 is equal to matrix C, which is 3 cross 3. And then we have F ABC. Yeah. And you want to find the inverse Clarke, then you can simply do F ABC equal to C3. So I'll just write 3 C inverse F alpha beta 0. And in this case, this is your inverse Clarke's matrix. And you can always do the inverse, right? So you can find the inverse already in the Google, or you can use MATLAB to find the inverse. Okay, and we will also give you inverse, so no worries. But if you remember from the Professor Eckel lecture, you would see that there is a multiplier here. There is a multiplier which is 2/3. Anyone remember? There is a 2/3 there, right? Okay, why do we have that? Anyone knows? But what we did is we just did the found the components on the alpha axis and the beta axis, and we got this matrix. Now there is this factor 2/3. Why do we have it? Anyone knows? Okay, then let's find it together. Let's find it together. So basically you will see this 2/3 also. You will see also this 2/3 factor, or it's up to you, I would say. I would say it's up to you. You want to multiply with half, you want to multiply with 3, you want to multiply with 1000, I don't care. You will see something. So it's just a scaling, you know, it's just a multiplying by some constant. So I do not care much here, because when you do multiply with something in the Clarke transformation, for sure you will see that multiplication in inverse Clarke transformation, right? If you multiply something in Clarke transformation, you will see that in inverse Clarke transformation, and they will cancel out. So even if you keep this 2/3 over here, if you do the inverse Clarke transformation, what's happening? Indirectly, you are multiplying by 3/2 there. So it is also canceling. So it really does not matter what do you put there. But it matters if you see in DQ frame, if it matters if you see in alpha beta frame. But if you want to see from ABC to, like if you come from ABC and then go to DQ, and then from DQ you go to ABC again, you will literally do not see any difference, because they're in Clarke transformation or the Park transformation, and the inverse, it's all canceling each other. But when you see in DQ or alpha beta, it makes difference. Okay. And there is a reason why we have 2/3, just not 1/3 or 2 or 5. So it's just to make our life easier, we have something there. And I'll tell you which life it makes easy. So let's see that. So as I always, I told in the beginning, the main purpose of transformation is to make our fundamental components DC, right? The fundamental so we want to focus on fundamentals only. There are other harmonics, so we cannot make everything DC, but for sure we can make our fundamental components DC. So fundamental component means we can assume, so let's say just positive sequence, right? When I say fundamental, I mean positive sequence. So for positive sequence, your FA plus FB plus FC is what? 0. For positive sequence, do we have 0 sequence there? No. So the positive sequence, it is like this. You have this this FA, this is your FB, and this is your FC. And if you try to add all together, their magnitudes are same and 120° apart. If you try to add all this together, you will see that their resultant is going to be 0. Okay, so that is why there is no 0 sequence component in positive sequence component. Okay, so if this is the case, then let's find the F alpha component. So the F alpha, what we know is, it is from 1 minus, like FA minus 1/2 FA minus 1/2 FC. So let's remove this factor here. So I don't have the factor, right? We just got it from the resolving the vector, and we have this equation, right? We saw it in the top also. We wrote it on the top. It's the same equation. Is that okay? And let's solve this. Yeah, there is again a mistake. This should be B. So let's solve this again, and with this condition. So we can rearrange and write it like this: FB plus FC And this FB plus FC, can we write minus FA? Is it okay to write minus FA? If zero sequence component is 0, then what we can write? Minus FA. And this is become FA plus FA by 2, and then this gets 3 FA by 2. So do you see a factor over there? This is the extra factor we have, right? This is 3 by 2. So if we wish that our alpha component value, like we want to do transformation such a way that our alpha component value is exactly the first phase, then we have to multiply this with 3 by 2, right? 2 by 3, right? So let's say if we multiply this whole thing with 2 by 3, then it will become 2 by 3 F alpha is equal to FA. So it means if we make this as our new alpha definition, F alpha dash. So this is just a definition, the new definition we are choosing, or the new things. Like in physics, you might have studied. Like I can consider. Let's say this is a line. You can consider 1 centimeter like this, or if you want to make your whole new system, let's say not SI system, you want to make. Let's say I want to make GAN system. So there I would make this is not 1 centimeter. I will make this as 1 centimeter. It's up to me, just the way you write. So this is your new definition. The F alpha dash is your new definition. And in this new definition, the FA component is exactly same as F alpha dash. And that is the reason why do we have 2 over 3 there. So that is why, what do we have? This F alpha dash, F beta dash, and F 0 dash as equal to 2 over 3. 2 over 3, this matrix. Okay. So it's 1 minus 1 by 2 minus 1 by 3, 0 root 3 by 2 minus root 3 by 2, 1 by 3, 1 by 3, and 1 by 3. It's FA, FB, and FC. Is it? Yeah, but for negative, for this zero sequence, we just want to find the zero sequence the way it is. We also don't want to find zero sequence which has other value. So for zero sequence, we would keep things same. So it means so now if we see the zero sequence in this way, it is going to be this plus this. So I just multiply here with 3 by 2, 3 by 2, 3 by 2. So it will be 2 by 3, 1 minus this, and 1 by 2, right? So like our zero sequence also should be like a zero sequence, right? It means we want to see our F0 is equal to FA plus FB plus FC by 3, right? So if you multiply 2 by 3 over there, then it changes it. So we have to multiply with the reverse, and then we have this matrix. Got it? Cool. So this 2 by 3 factors actually helps in alpha beta frame. It helps in alpha beta frame so that we can get our F alpha and F beta magnitude same as the magnitude for the ABC system. So that's the main reason. Okay, so our new transformation, new Clarke transformation matrix is C equal to 2/3, and it's 1 minus this thing, 0 √3/2, √3 by, this should be minus, yeah. Yeah, if you see some mistakes in writing like minus or FA, B or C, then you please tell me that. So this is our the Clarke transformation matrix. Okay. Okay, and now if you see just for fundamental component, we can write our F alpha equal to FA, right? For fundamental component, what we can write? F alpha equal to FA. So we can write another matrix also, like the simplified matrix. The simplified matrix would be like 2/3. We just make 1 0 0, then 0 √3/2 minus minus √3/2, 1/2, 1/2, and then multiplied with your FA, FB, and FC. We can also write like this. Is it okay? Because just now we saw our F alpha is equal to FA for positive sequence, right? So this is your simplified Clarke transformation. So which one you like more, the simplified or this one? Which one? So as I said, I will share this document with you. So which one you like more? The simplified or the actual one? Or you just don't know? The simplified? Yeah, never use that. Never use that. Because if you see, the assumption for this is what? The zero sequence component is 0, right?
0. Yep.
Which can be, which cannot be also. So I would say in zero sequence, if you assume zero sequence is 0, it does not make sense to use this one, right? Yeah, because we assume the zero sequence is 0, then it does not make sense to write a formula for 0. Okay, so I would say not use it. That's the main purpose to tell you that why we are just doing this simplification also, because many places we see students using this because they feel really good that they don't have to do this calculations, and they tell, okay, now FA is equal to F alpha, one problem is solved, and then we just have F beta, we have to just do something for that. But don't use it. I would say use this one, because if you have zero sequence in a component, you will see trouble, which we will also see in the half part of this exercise. Okay, so this is about Clarke transformation, and now let's see how we can do the part transformation. So there is a very traditional way people explain you, but I'll try to explain you mathematically, and you can maybe understand why do we do such multiplication there. So for that, For that, let's solve our FABC, like FABC in terms of F alpha and F beta. So now we will create a definition like F vector. We write the below some line to denote it's a vector. And then I write here S. So it means stationary frame. Stationary frame is your which frame? The alpha beta, right? The alpha beta frame is your stationary frame. So you can write it like F vector alpha beta also. So it's your wish. Whichever way you want to write, it's fine. So this we will define like this, F alpha plus J F beta. F alpha plus J F beta. What is J? It's just a imaginary component. Yeah, so this imaginary unit basically, and this F beta is imaginary on the imaginary axis, and this is on the real axis. Okay, so let's simplify these. So you can write this F alpha as 2/3 into so 2/3 into these things. So it is going to be 2/3 FA minus 1/2 FB minus 1/2 FC plus J 2/3 into, we have √3/2 √3/2 FB minus √3/2 FC. And let's solve it. And for simplifying this, let's assume our positive sequence only in the system. Okay, so let's assume we have positive sequence in the system. So assuming FABC has only positive sequence component. So it means we can write FA as some magnitude. So let's say F hat is a magnitude, cos into yeah, we can write cos omega t plus phi. So let's say some initial phase. FP is equal to F cap cos omega t plus omega t minus 2π/3 plus phi naught. FC is equal to cos omega t plus 2π/3 phi naught. So this is our positive sequence three-phase voltages. I think you have been, I think you are already familiar with these things. I just added this phi naught, which is the initial phase. So this initial phase can be anything. And now I would like you to solve this so we can do it together, but I would skip that because we have very less time. So what you can do is you can just substitute these into the above equation, and you would see that the F stationary is going to be F hat cos omega t plus phi naught plus J F cap sin omega t plus phi naught. This is one exercise for you. So just some trigonometry, you have learned this in your high schools, and then you can just do it. If you get stuck with any place, then but do it for sure, okay? You do it by yourself. If you get stuck with that, then you can come and ask the problem. But you will get something like this. So the interesting thing is, if you see already this thing is looking similar as FA, right? So the real part is already looking equal to the FA. So it is just about this F beta you have to solve. And this F beta, you will see it will be like that. So if you see this thing, so the real axis or the alpha component is like the cosine function, and the imaginary axis is like the sine function. So we can take the common, and then it becomes cos omega t plus phi naught plus j sine omega t plus phi naught. Anyone knows how we can denote this? E power j theta, correct. So we can write this as f cap into e power j, whatever you have inside the bracket. So it is j into omega t plus phi naught. So it is because e j theta is your cos theta plus j sine theta. Everyone know this? Is everyone familiar with this thing?
Yes, sir.
Yeah, so this is using Euler's notation. So for positive sequence, what do you see is, you see this. So I will write it like this now. F cap into e power j theta positive. So where theta positive is your omega t plus phi naught. Is this also okay? Yeah. Do you have any question until now? Is there a question? If you do not know question, then it's pretty easy to explain further now. Now I have a question. I want to make, so when I say DC, it basically this thing, right? This is your DC, right? This is your amplitude. This is your DC quantity which we want to know. And we want, and this, because of this e power j theta, we have a AC component, which is your cos theta and the sine theta. We just want to get the DC component. We don't want the AC component. So what you can do to make this DC? So like, let's say you can multiply with something, you can divide with something. So which factor do you think you can multiply and make this DC? It's not very difficult. We want to eliminate this e power j theta. With what you should multiply? Exactly. We should multiply with e minus j theta, e power minus j theta, right? So we multiply this with e power minus j theta. And this is now going to be your rotating frame component, which is equal to your dq frame component. And this is equal to your f stationary into e power minus j theta. So I will not write positive here, but that's a concept. You multiply with e power minus j theta, right? So I'll not write a positive here. I'll just write e power minus z, let's say theta p. Theta p is like the part transformation angle. So p is from part transformation, which is transforming from alpha beta to dq. So if theta p is equal to theta positive, then what we can write is, this is f dash into let's see, let's do like this. Yeah, okay, for time being, let it be like this. So if it is like this, then for this stationary, we can write like f cap into e power j theta positive, and then we have this into e power minus j theta positive, and these two cancel out each other, and then we have this f cap. And for sure, this is your DC value. There is no e power j theta, so it means there is no cos value, there is no sine value. You just have your DC value. Sounds beautiful? So this is the main purpose. This is the main understanding. Why do we do transformation? Because we always want to control or to regulate the fundamental positive sequence power. The negative sequence component we gave because of some disturbance. in the system or because of the fault. And zero sequence is also we do not want to have in the system. So basically we always like to have this fundamental component and control it. And then the harmonics and all, which will always be there, but we never want to be there. But we want to control these things. And hence we have a DC value here now. So how do we do the alpha beta to DQ transformation? So this was the purpose, but now let's see the more how we do it. So what we saw now is F rotating frame, which is also equal to your F DQ. We get it by multiplying this F alpha beta into e power minus j theta p, right? We do it like this, right? We have this alpha beta frame and we alpha beta value and we multiply with e power minus j theta. And why we multiply with this, I think you know now. So, okay. So let's solve this, no? So we have this F alpha plus JF beta. And this we can write like cos theta p plus minus. Now we have a minus, so minus sine theta p. I can write like this. Is it okay? Yeah. So let's solve this. So we have this F alpha cos theta p. And then we can just do like this. So I'll try to separate the real and the imaginary part. So we have the real part like this and plus j. J is F beta cos theta p. And then minus F alpha sine theta p. Is this correct? Is this correct? It's fine, I guess. So now we can again write this F vector dq as fd plus jfq. And we can equate the real and imaginary part. So the real part is fd, which is equal to F alpha cos theta p plus F beta sine theta p. And then fq is your F beta cos theta p. Okay, I'll write F alpha first. It looks nice to see alpha first. And then we have F beta cos theta p. And if you want to write in a matrix form, you can write like this: cos theta p, sin theta p, sin theta p, cos theta p as F alpha, F beta. Have you seen this matrix already? Have you seen this matrix in Professor Eccles' lecture? You have seen, right? Now you know from where it comes. So there are many ways you can derive actually, like you can derive it from the state space representation again. Yeah, but this is how, so you derive from many ways, you will get the same result. And of course, if you want to find from alpha beta to, like we want to find alpha beta component from DQ, then you can just take the inverse of this. And inverse is going to be easier. It's, I think the minus we get here and then cos theta p F. And this, if you write in a complex form, so this is not in a complex form now. So this matrix is basically inverse of this. And you can, I think the inverse which I have written is correct, but you should be able to find it easily also. And if you want to write in a complex form, so in complex form, what we saw is the F dq vector is f vector alpha beta into e power minus j theta p, and this complex form would be also very simple. So it's just positive over there, right? F dq into e power j theta p. Simple. So you can do the transformation in complex form also, or you can do in a matrix form also. It's your wish. I will not say anything. Is this okay? Do you have any question now? Okay, so I think if so now we have done the transformations, and let's understand the physical meaning of this dq transformation. Why we have dc, but not understanding using just equations, but let's understand the physical meaning of this. So what we have seen is this is our alpha axis, this is our beta axis, and this is your a axis, c axis, and b axis. This we have already seen, right? And I also tried to show you that the resultant of ABC rotates in anticlockwise for the positive sequence. For positive sequence component, what we saw, our resultant vector is rotating anticlockwise, right? So it means let's say if this is a resultant vector, which is your v alpha beta. So you can write it like a v vector stationary frame also. Like you can also write here v alpha beta as v is stationary, s over top. So it's just a notation. You can use any notation you like. And we know this is rotating with speed omega, right? We saw this here. We saw this in the beginning. So we saw in the beginning itself, which is this diagram, which is basically this diagram. And you can see what we saw, that the resultant vector was rotating this way in anticlockwise, right? So that is what I'm trying to say. So this is what I'm trying to say. Our resultant vector is rotating anticlockwise. In your high schools, you might have studied the resultant vector. Maybe I don't know what's the name in German, but it's a relative velocity basically. The relative velocity is like, I'll give you an example. Let's say we have a train, not train, let's say car. It's your friend's car, and you have also a car. If it's moving in the same direction, but the velocity of both is different, right? So you would see this. If, for example, let's say the velocities are same. So the velocities are same. So it means car 1, car 2, it's moving with 10 meters per second, and this is also moving with 10 meters per second. So do you think for them, the whole system is stationary, right? Like they can see each other. So if a person in car 1 sees a person in car 2, they will notice that it's not moving. They'll notice they both are not moving. They are just sitting. They are just sitting they are just stationary with respect to them. But they are moving with respect to the tree or the buildings, right? But when they see each other, they see each other the same, or in the same place always. If they just forget the whole world. So this is relative velocity. It's like a concept. But now let's imagine the car is moving in opposite direction. And the person in one car observes the person in another car. Then they will see actually they are moving with a double speed. then the person in one car will assume that the person in another car is moving with 20 meter per second. It is not moving with 10 meter per second. That person will see the car is moving even faster, because that is also going away and this person is also going away. So their velocity adds up when they see each other. So this is your relative velocity concept. And so whenever we define the relative velocity, we write like, yeah, so here V does not get confused with the voltage. Let's say U is your speed, or the velocity, I would say, not speed. Here it's a vector quantity. So V12 is your relative velocity, which is V1 minus V2. Okay, V1 minus V2. So if they are in the same direction, their velocity cancel out each other. So their relative velocity is 0. And if they are in opposite direction, the one velocity is negative, one is positive. So they add up each other. So this is your relative speed, relative velocity. Okay, so this was in a linear motion. This is in a linear motion when a person is going straight. What if it's rotating? What if it's rotating? You are rotating, let's say in a circular motion. Let's say someone is rotating in a circular motion. So what we saw is this speed, this vector, this resultant vector is rotating anti-clockwise, right? So if we just sit on top of that vector, so you will also rotate. That's of course, right? You will also rotate. But for you, is the V alpha vector magnitude, does it change? You'll just always see this like the person same, right? Let's say there are two persons sitting on this, and you are the one person, another is your V alpha beta magnitude basically. So when you rotate with the same speed, you would see that V alpha beta is always there. It's always the same. The magnitude is always the same. It's not changing, right? So the thing is, what happens, this is the concept we use. This is the actual concept we use, the relative concept. I will use green color maybe. So this is the concept that we align our D and Q axis with a rotating vector direction. So it means our DQ axis is rotating along with the resultant vector. Right? So our DQ axis is itself rotating along with the resultant vector. And hence we see there is no speed, right? The total resultant speed is omega 1 minus omega 2, and there is no speed. It's the same with the relative velocity, and it's the same with the relative speed also, the relative angular speed. So the vector is rotating with omega speed, and we also rotate with omega speed in the same direction. So it means we just don't see omega. There is no omega. So when there is no omega, what do we call the quantity? DC, right?
DC.
There is no omega, it means we are getting the DC quantity. So here is, yeah, so if you want to understand the physically what's happening, then we try to rotate along with the resultant vector. We try to rotate along with the resultant vector and in the same direction. Okay, is this clear? So this is all for fundamental component. This is all for fundamental component. What if you rotate opposite direction? It means we do not rotate our DQ axis in the, so in this case, it's rotating this way. Okay. Now, let's say we have a negative sequence component. Let's say what we have? Negative sequence component. So for negative sequence component, I will draw it again. So this is for positive sequence. Positive sequence component. Let's do it for negative sequence. So this time I will just draw your alpha beta. This is your vector. This is your resultant vector, f v alpha beta. And for the negative sequence, what do we know is it rotates in clockwise, right? We also saw it. So we saw it here. Yeah, we saw it here. For the negative sequence, what we saw is the resultant vector is rotating in clockwise direction and with the speed omega. But what we know is our DQ frame is rotating in anti-clockwise. So this is, let's say, omega 1, omega 2. So what do you see? The DQ frame will have a DC component or AC component?
AC.
It will have an AC component because they are not rotating in the same direction. They are rotating in different direction. And which frequency it will see?
Omega 1 minus omega 2.
Omega 1 plus omega 2.
Plus,
You have to.
yeah.
So the formula is what? Omega 1 minus omega 2. But if you see here, their direction is different, right?
Yep.
So if I just want to see the magnitude, so let's say this anti-clockwise is positive, and then this would be like omega 2 magnitude and then minus. So it will be omega 1 magnitude plus omega 2 magnitude. Right? So you would see omega 1 plus omega 2. So if both are 50 hertz, then what frequency you will see? 100 hertz. So in DQ frame, if negative sequence component is there, you will also see 100 hertz component. So if there are both, let's say there is a positive sequence, there is a negative sequence, then which frequencies you will see in the DC, in the DQ frame? So for positive sequence, you will see DC. And for negative sequence, what you will see? For negative sequence, you will see AC, which is 100 hertz component for this case. So let's find a general formula. Not for the fundamental component 50 hertz, but just a general formula. It will just take 5 minutes, then we'll go for a break. And then we can do lunch and we can continue again. So let's find a general formula now. Hello, yeah. Yeah, so I'm trying to record it so you can see later. Okay, cool. So let's find a general formula. And it's going to be simple, I guess. So what we saw is the f alpha beta, the vector, is equal to f cap e power j omega t plus phi naught. We saw this earlier, right? Do you remember? I'll show you where it is. It's here. It's this one. But you should remember that this is only for positive sequence, okay? Because I assumed only positive sequence. So I'm just talking about positive sequence now. So this is for positive sequence, and we get this formula. And that is what I have written down here. Okay, cool. Now, and in DQ, what do we do is we multiply alpha beta with e power j minus j theta p, minus j theta p. And now let's assume this is your omega 1. So I'd say positive sequence with omega equal to omega 1. Just to make you clear that this is another omega. And let's assume this, okay, so one more thing, this part transformation angle, this can be anything. Again, it can have any frequency, it can have any phase difference, so it can have anything, okay? So be clear, this is all again an input, and you are free to define the input the way you want. So let's say this is omega t plus I used phi, I used theta, there is, let's use gamma naught. Yeah, anything, just want to make some variable. So this is the initial phase, this gamma naught is the initial phase, this is your different omega. And if we substitute these two, what you would see is e power j omega 1 t plus phi naught into e power minus j omega 2 t plus phi naught. And you can solve these two, and what you will get is omega 1 minus omega 2 into t plus phi naught minus gamma naught. Is this clear? Is this clear? Is it clear?
Yes.
Okay. And now let's see some cases. So this is your general formula. This is what? The general formula. So case 1, what we have is omega 1 equal to omega 2 and phi naught equal to gamma naught. So let's say they are all the same. Then what do we have is f dq is equal to f cap into e power 0. So it is just your f cap. And we can write this as like f cap plus j0, right? So what do we have is, we just have the d component. What we have? We just have d component and it is dc. We have d component and it is dc. Let's see another case. Omega 1 is equal to omega 2, but this time your phi naught is not equal to gamma naught. It can be any value, I don't know, but let's say it's any value. So what we'll have is f dq is equal to f cap. So this omega term will go away, and we will just have e power j phi naught minus gamma naught. So tell me, is there a frequency in the, is there AC term here? Do we have any AC term here? Do we have any AC term here? You can guess also, yes or no? No. So who thinks there is no AC term? Can raise your hand. Okay, one person. So there is no AC term here because you do not have omega. It's very clear, right? You do not have omega into t, so there is no AC. So this is only DC. There's no AC. And the interesting thing is, you should always, you should actually know this, that here in this case, your D and Q components, they both have some value, right? So many people think in DQ frame, we just have D value. We do not have Q value. Many people think that the D value itself is your magnitude. No, you can have Q value also. But when do you have a Q value? For fundamental component also, you can have a Q value. So that Q value is decided by this phase difference. So with your part transformation, what's the phase difference? And then your three-phase positive sequence angle, what's the phase difference? So this is your, so now you have Ft is equal to F cos phi naught minus this thing, and Fq is your F vector sine phi minus this thing. But if you want to find the magnitude, you just want to know the magnitude, then the magnitude is always, if you find the FDQ magnitude, you will see it is always F dash, like F cap. It's very easy to find, right? You can just find the square of this and then plus a square of this. So this FDQ magnitude means square root of FD square plus FQ square, right? And you can solve this, you will get this one. So if you want to find the magnitude of voltage or current, for fundamental component, you find the magnitude of dq component. Just don't assume that the d component magnitude is equal to the magnitude of system. So you should always find the magnitude of dq component, not d. In case 1, it is true that the magnitude of fd is equal to the actual magnitude, but in general it's wrong. Okay. Case 3. Now we do not, omega 1 is not equal to omega 2 and phi naught, let's say equal. It does not make sense, or maybe it makes sense. In the beginning we can have anything. So let's say we have like this, so it can be like this, or I will write like this. Well, let's say we'll make that case 4. That's okay. So f vector dq will be f cap into e power j omega 1 minus omega 2 into t. Is there AC component?
Yes.
Yeah. Only AC. So there is no DC, okay? Case 4. Omega 1 not equal to this, and then phi not equal to this. Now you tell me, is there only AC or both? For sure there is AC, so you should tell me whether there is only AC or there is both DC and AC.
There is
Both? Okay. But it's not both, it's AC again. Why? Because what we know is, if you want to write it like this, so you will write cos omega 1 minus omega 2 into t plus phi naught minus gamma naught. So it is inside the cos, right? So it has only AC. So that is why I was just thinking whether to make this 2 condition or not. Okay. So now you know that which frequency in the DQ can be there. If there is a frequency difference, there is a phase difference, and all those things. Is it clear until now? So I have a homework for you. So related to this derivation. So now the homework for you is, now we will consider also negative sequence component in the system. So till now there were only positive sequence, but now let's consider the negative sequence also. So FABC has positive, negative, and 0 sequence component. So it means our FA will look like F plus cap phi naught plus F negative cap cos omega t plus phi 0 minus, and then plus F naught cap. So which one is positive in this? The first, second, or third? The first one is positive because I wrote positive there. The second one is negative. And the last one is zero sequence. So for the B phase, we know that in the positive, we lag by 2 pi by 3 angle. And in negative, we lead by 2 pi by 3 angle. And for the vector C, for the phase 3, for positive, we lead phase A by 2 pi by 3. For negative, we lag phase A by 2 by 3. So the homework for you is to use the generalized formula. Okay, I always tell, don't use the simplified Clarke transformation, use the general formula and find this F alpha, F beta, F naught. Find this. It's your wish. You can write in a matrix form or you can do in a complex form. You know, you are free to write in whichever way you want. This one and FD, FQ. Of course, the zero sequence is same, so I'll not write it again. Or you can write in vector FDQ, which is your FD plus JFQ. So you should find the general formula for this. So for a positive sequence, you already have the formula, right? For positive sequence, you have this. Just have to change it, right? But you just have to do the calculation for which sequence? The negative sequence. Because zero sequence, you don't need to do anything. So this is your homework, and your, of course, theta p, I will keep it the same way. So I can write here omega 1. So let's say this is omega 1, and your theta p is omega 2t plus gamma naught. It's the same, right? Yeah, omega t 2t plus this thing. So yeah, so you should find, you should solve these things. And at the end, what you will see for positive sequence, the both omega will subtract, omega 1 minus omega 2. I mean, you will see this. You will see this thing for positive sequence, and for negative sequence, you will see omega 1 plus omega 2. You should see omega 1 plus omega 2. If you do not see that for negative sequence, then you can assume your derivation is wrong. Okay, so this is all about the transformation, and if you have any questions, then you can ask now. This is all about theory for today, and we will do the practical. Like practical means we will do the MATLAB exercise after the break, and we will have half an hour break, so you can go to Mensa and have the lunch, and we'll meet here again in half an hour. So I would say 1:40. Is that okay? Is that okay for everyone? We meet at 1:40. Okay. Okay, then see you soon.